Let's review exam 3, fall 2020. Of course, because of the pandemic and hurricanes, not much was covered, but let's review what was tested. So question 1, the energy below is typical for, okay, so in the diagram, there's several things I see. So our reactants are right here, our products are here, and up here is a one transition state. So it's only one TS. Whenever you have one transition state, it means both reactants were involved in making it. So this reaction is bimolecular. And if it's bimolecular, it's either E2 or SN2 for our course. So yeah, that goes with E2. So it's true. It will be true also for SN2, but that's not what the question asked. Okay. Question 2. Which beta hydrogen would be removed by a strong base in E2? So we have this structure, and you see that your leaving group, okay, the leaving group is toward based on the wedge bond. So the best hydrogen to be removed is one that is anti-coplanar, which is hydrogen B, because it's opposite in geometry. See, that's towards and this is away. That goes with the 180 degrees rule. I think we call it anti-periplanar rule. Some authors will call it anti-coplanar rule, which is just like the difference is just in few degrees in the two. So the one to be removed is B, not C, because C has the same type of bond. The base will always remove. So if you use a base, a strong base like OCH3-, is gonna remove a hydrogen that has opposite orientation to the leaving group. So the base will take that hydrogen out, this bond makes a double bond, and of course the leaving group leaves. Okay, so the key point here is that true? Okay, question 3. What is the rate equation for the reaction below? So the only way to tell the rate equation is to look at what you're provided. Obviously, this is a tertiary alkyl halide, which obviously should not do SN2 because it's hindered on the backside. And I see this reaction is substitution. So in substitution is either SN2 or SN1. So since this guy is tertiary, it's not likely to give you SN2. Instead, it's gonna do SN1 going through a carbocation. And then, of course, the methanol will attack and be deprotonated to give you the product. So the thing is, looking at the arrow, you are given methanol. This is obviously weak nucleophile, which is consistent with SN1. It's also a weak base, but there's no elimination here. So E1 is not expected, it's SN1. And also, it's gonna play the role of a solvent. It happens to be protic solvent, which does not go with SN2. So the answer is SN1. And we know the rate equation for SN1 has to be unimolecular, only one molecule, which happens to be the A molecule that will play a role in the reaction, not the B, which is the methanol. It comes later to do the reaction. K here, I told you in class, can only be determined. It's a number that can only be determined by experiment. Question 4. I see a strong base, I see heating, I expect E2. So, because the base is small, it's not the tert butoxide, I expect the Z product, which means the more substituted double bond will be favored. So I have this beta hydrogen, or either of these two. I say either of those because they're both sitting on metals. I'd rather take out this hydrogen that's sitting on a more hindered carbon, and that's gonna give me the ZF product, which happens to be that. So this is tri-substituted. You see, there's 3 alkyl groups. So this is tri-substituted. If you take out one of the other one, this will be the product. This happens to be di-substituted. So this is gonna be the major product, and the other one will be the minor. So let's read the question. The question wants the major, so the answer here is choice C. Question 5. What is the major product to the reaction below? I see CN. I told you usually CN is a bullet nucleophile, never wants to play the role of a base. And this is secondary alkyl halide, so it's likely also to do SN2. No worries about sterics. Okay. So I know that NaCN can be written as Na plus Cn minus. So this is the nucleophile that will do a back attack. And because there's a back attack, there's inversion of configuration. So the answer will look like this. Which obviously is choice A. Br falls off. And I know that because this is SN2, because this is nucleophile only, and it's a strong nucleophile, and this is secondary alkyl halide. So it's possible, you know, SN2 can work with primary alkyl halide, secondary. The tertiary never does it, and a halogen on sp2 carbon will never do SN2. A halogen on sp carbon will never do SN2. The best here is gonna be the least hindered, which is methyl halide. So secondary alkyl halide is possible to do SN2. The answer is A for question 5. For question 6, what is the major product to the reaction? So it says 1 equivalent of methanol. If there is truly 1 equivalent of methanol, I'm not going to draw the mechanism. All you need to know is, let me choose a different color here. The shortcut I gave you in class was simple. The OCH3 plus, or the O group, O part of the alcohol is going to be added. This part will be added onto this carbon, and this hydrogen will end up on the oxygen. You open up the pi bond. So basically this is going to be your product. Okay. This would have been your product. So you would have added OCH3 and make an OH, but just simply adding the OCH3 part onto this carbon and take the hydrogen onto the oxygen. This is called hemiacetar. Hemiacetar. So if it were 2 equivalents, then you get an acetar. So you can obviously see that none of these molecules look like what I drew, so it's none of the choices. That's the answer for question 6. None of the choices looks like our product that I drew. So 7. What is the product to the reaction below? So this is what we have. It says 1 equivalent of methanol. I already gave you the shortcut. So again, the H should end up on the oxygen. The OCH3 part should be added onto this carbon. So I would expect those two to be added across the aldehyde, and the hydrogen ends up on the carbonyl oxygen, this guy, and the OCH3 is added onto the carbon of the carbonyl, and then you simply copy the rest. Of course, there's a hydrogen here too. It's just not drawn in the question, but it's implied. So this would have been our product, and that basically happens to be the structure B. The two hydrogens are right there. Okay, so the answer is B for question 7. Question 8. What is the product for the reaction below? It says excess. So question 8, you are given a carbonyl and a H, and you're told you have excess methanol. So excess methanol would imply you have more than two and more. So basically for this one, it's simple. The shortcut, the two OCH3s will be added, replacing the carbonyl. Okay, so I would just give you the shortcut. Again, we did all these mechanisms in class. I'm not gonna do those mechanisms right now. You can review the recorded mixed videos. So the shortcut, OCH3s will replace the carbonyl. So this is called an acetal. So instead of having a hemiacetal, the OH is replaced by another OCH3. So going with this structure, you see here we have CH3. The difference between this structure and that, here you have H, here you have CH3, but it's just one more step replacing the OH in this problem to give you acetal. Okay, so let's see question 9. Question 9 is a Grignard. So with Grignard, it's still an addition reaction. You're adding an alkyl group on to the carbonyl. So let's say that this is your alkyl. So yes, you have CH3. So the CH3 is the alkyl part. So I'm gonna write it as a carbanion. That's what I told you in class. The rest will be a cation. So you can imagine the methyl group attacking the carbonyl. This opens up, picking up the proton because it says then add H+. So basically, you're gonna end up with the CH3 that attacked the carbonyl and the hydrogen added onto the oxygen of the carbonyl, and then the other hydrogen is still there. So you're making an alcohol. This is an aldehyde. It's giving you a secondary alcohol. Okay, so this happens to be structure C, because if I don't write the CH3 showing its hydrogen, then you're gonna see it's structure C. Okay, moving on to question 10. Question 10. So this is a dehydration reaction, and it's definitely by E1. We did dehydration with E1. So basically what happens is the acid activates OH to leave, because leaving groups must leave as weak bases. So you'll get activated alcohol. Then this will fall off. Okay, once it falls off, there's a problem. You get a primary carbocation, which you rearrange. Okay, primary carbocations are not stable, so they rearrange. And now here you have two hydrogens. So after the hydrogen shift, we call this H shift. After H shift, now you'll have three hydrogens. It rearranges to be more stable. This is now a tertiary. That's tertiary carbocation. There's 3 carbons across the C+. That's why it's tertiary. Now the tertiary can now do E1, where you use the water that fell off. See, this water fell off. I should have written here plus H2O. It's used as a weak base. The H2O is used as a weak base to take out a beta hydrogen. You make a double bond. You get the Zaitsev product. E1 always gives you Zaitsev product. And it's going to be the major, because this guy is tri-substituted. There's a carbon there, carbon here, and carbon here across the double bond. So it's tri-sub and tri-substituted, and it's the major. product. Now, if this undergoes E1, then you'll be using your water. Instead of the shift, you'll be using your water to take out this hydrogen. You make a double bond, and that's how you get this product. So you have these two options. This happens to be option A, structure A, and this happens to be structure C. You can see it right there. So the answers I was looking for is A and C. Those were correct, structure A and C by E1. So this is unimolecular elimination. So let's go to question 11. What is the product? Here you're just replacing the OH with a Cl. I told you the shortcut in class. So you are chlorinating the molecule, replacing the OH with a Cl. Chlorination of alcohols by this one undergoes SN2 process to do this. You're substituting OH with Cl. So the answer is C. And then PCC is a mild oxidant. So if you're given a primary alcohol like this, and you add PCC, the primary alcohol is just gonna be oxidized to the aldehyde and it stops there. If this was chromic acid, or what we call Jones, if this was Jones, this is C2CR207, I think. If this was Jones, either it's an acid with CrO3 or written like this, then you don't stop at the aldehyde. It would go all the way to the carboxylic acid. So the answer for question 12 is an aldehyde, which happens to be structure C. The hydrogen is there, just not drawn. Now here's the Jones. If it's Jones, you get the carboxylic acid, which is D, which is what I've shown here for question 13. Question 14. You are given an alcohol. Whenever you want to name an alcohol, prioritize the carbon bearing the alcohol. That's our numbering. We have a methyl group on carbon 3. So the name is 3-methyl. And then you have to specify the position of the alcohol. It's on carbon 1. And the alcohol has 4 carbons, so it's but. And then it's an alcohol, so butanol. So that's the name for 14. Let's look at 15. If you were to name this ketone, prioritize the position of the carbonyls. So I'll start numbering from the left. So I have 2 metals on carbon 4. Those are the 2 metals. So I would specify 4 dash to separate the numbers from the alphabets. We say dimethyl because there are 2 metals. There are 5 carbons, so it's pentan. It's a ketone, so I give the suffix ONE. So the name is 4,4-dimethyl-pentanone for question 15. 16, it's an aldehyde. So it will end up with the suffix al. 1, 2, 3, 4. There are 3 metals on 3rd carbon, so it's 3,3-dimethyl. 3,3-dimethyl, and then I have the aldehyde on the 1st carbon. So we don't need to say, aldehydes are always at the end of the chain. We don't need to say 1-butanol. So we'll just say butanal, because it's an aldehyde. 3,3-dimethyl butanal. We have another aldehyde. Okay, but this time the aldehyde has a ring, so we'll give the ring going with its just alkane name. It happens to be cyclobutane, and because it's an aldehyde on an alkane ring, we just finish by giving it the name carbaldehyde. So cyclic aldehydes are named specially they're given special names. You just give the, see, these are 4 carbon ring, so it's cyclobutane, and then it's an aldehyde, so you add the suffix part carbaldehyde. If it's 5-membered ring, it will be cyclopentane carbaldehyde, and so on and so on. So let's do 18. 18 is a diol because there's 2 OHs. So we prioritize position of OH. So it's 1,3 butane diol. You give the alkyl name of the chain and then you write diol. Otherwise it would have been butanol if it was only 1 OH. Okay. Question 19. This one no need to draw. We need to rank from highest to lowest boiling point. The more the OHs, the higher the boiling point, because you have more chances for hydrogen bonding. So A has high boiling point than B. B has high boiling point than C. There's no OH here. So answer is A. Moving on. Which of the following was the best for SN1? Okay. So you know SN1 likes protic, polar solvents, and we define protic solvents that have we define protic solvents as solvents that have hydrogens bonded directly to oxygen or nitrogen or fluorine. So you needed to draw the structures of this. Benzene has no oxygen, so this guy is non-protic. And non-protic simply means aprotic. That's the word we use. The opposite of protic is aprotic. There's no hydrogens bonded directly to O, N, and F. Same applies to the next one, 2-propanone. It's simply the nail polish remover. My pen is acting up. So this is 2-propanone. This is best for SN2 because again it's aprotic. You don't see any of this type of bonds. Hexanes is just 6 carbons. 1, 2, 4, 6. All you have here is carbon hydrogens. Again, this is aprotic. So the answer is 2-propanol because that's an alcohol. Okay, this guy is protic and it's polar. So that's the best for SN1. We explained in the lecture why you want polar protic solvents for SN1. Okay, I think that was question 20. So that was the last part of the test, exam 3.